Hey, hello students. All right, I got another question from number 9 here from chapter 4. And it says this: the Earth orbits around the sun every 365 days at an average distance of 1.5 times 10 to the 11th meters. The Earth's mass is 6 times 10 to the 24. Okay, so then A, how many seconds does it take the Earth to orbit the sun? Now, I guess the first part of this is to know that it takes 1 year for the Earth to go all the way around the sun. So I'm going to start there. And then really this first one is a unit conversion. So let me take us back to chapter 1 and say that there are 365 days in a year. So when you multiply that, the year is going to cancel off, and of course that's going to give you the number of days. Then we could say something like this: there's 24 hours in a day, and then of course days would cancel off, and that's going to give us the number of hours. Then we can take the next step and multiply it by 60 minutes in an hour, and then the hours cancel off, so that would be the number of minutes. And then finally, the last step is 60 seconds in a minute. And so if we multiply all that out, we now have the number of seconds. And by the way, kind of a side note that us crazy physicists like is pi times 10 to the 7th. And so I think it does come out to be 3.15 times 10 to the 7th seconds. But since you're not expected to have that number memorized, let me give it a try here with our calculator. All right, so it would be 1 times 365 times 24 times 60 times another 60, and there it is, 3.15. Let me just count the zeros. 1, 2, 3, 4, 5, 6, 7. Yep. And so 3.15 times 10 to the 7th. All right. So that's the part A, and that's really more of a unit conversion from back to chapter 1. Then it says, what distance does the Earth travel in 1 year? Okay, well, this really takes us back to our math class and a little bit of science. Like, for first here, you needed to know that it took 1 year for the Earth to go around the sun. The other thing you need to know here, I guess, is that the Earth goes around in a circle, or at least nearly a circle, and that the circumference of a circle is 2 pi r. So there's the 2, there's the pi, and then the r is given. That was the radius, and says there's an average radius of 1.5 times 10 to the 11th meters. All right, so again, if I grab my calculator here, this would be 2, and then a pi, and then times 1.5 times 10 to the 11th, coming out to be 9.42 times 10 to the 11th meters. So that's the distance in meters. C, what's the Earth's average centripetal acceleration? Okay, so finally we get to something related to this chapter, and this chapter is Newton's second law. And one of the things we talked about here is the acceleration of an object going in a circle, and that's v squared over r. So this is the part that I lectured on in this chapter and said, okay, know this is v squared over r if anything's going in a circle. Now, of course, then that also means here that we need to get the v first. And that's why they really had you do A and B. And so even though A and B wasn't really part of this chapter, they were kind of helping you out, because if you know the distance it travels and the time it takes, you can just go distance divided by time. And so B gave us the distance and A gave us the time. So I'm going to take this distance, 9.42 times 10 to the 11th meters. And then divided by the time we got in A, 3.15 times 10 to the 7th seconds. And I guess I still have the distance here in my calculator, so I'll leave that alone. And then I'll just go divide, and then I'll arrow up and get the time. There it is. And paste it and hit enter. And so this is about 29,885. And I'm just going to round that to an even 30,000. So 30,000 meters per second. And so now I can use that up here. And I'll go ahead and write 30,000. Although, to be honest, I'm just going to put it in my calculator here and then hit square. And then divide. Okay, so I'll actually use in my calculator the 29,000. Okay, and then the R is that radius again. So that's that 1.5 times 10, what was it, to the 11th. All right, so I already hit square. And so now let me just put in the 1.5 times 10 to the 11, and it gives me an acceleration of 0.006 meters per second squared. And I should have shown you the units here. This speed squared would have been meters per second squared, and in the bottom would be meters. So in the top, we would have a meters squared, and then this would make a second squared. And then we have the meters from the average distance. One of the meters cancels off, and we end up with meters per second squared. And so that's our unit analysis, again, going back to chapter 1, where, we know we're going to get an answer in acceleration. We know acceleration is measured in meters per second squared. So anything that didn't work out right would tell us that we're doing something wrong. But since our units worked out right, that's not proof, but it's an indication that, hey, perhaps we're doing it right. And that's the meat of this problem, really, is the centripetal acceleration. There is one more, and it fits really in here with this chapter, or really maybe even last chapter. But then it says, what's the average force? And so Newton's second law says F equals to ma. They did give us the mass, so 6 times 10 to the 24 is the mass of the Earth. And then we need the acceleration, and that's what C was all about. So C is kind of the big one. It gave us the acceleration, and to do that we needed velocity, which we needed distance and time. So I'll just put 0.006 meters per second squared. Maybe I'll do the units first here. So a kilogram times a meter squared is a Newton. I still have the acceleration in my calculator, so I'll leave that there and then just go times 6 times 10 to the 24 and finish up with an answer of 3 point, and I'll round it to a 6 times 10 to the 22 newtons. So there are the 4 parts. Nice. Enjoy.